Here, we can see the vane airflow position sensor attached to the green airflow flap. This flap or vane changes position as air enters the actual air conduit. Hence the name, vane airflow sensor. The vane airflow sensor is a mechanical device that senses the airflow through a side-mounted flap position sensor. As the air enters the vane airflow sensor, the flap moves a specific amount. This movement is registered by the side-mounted flap position sensor. As the flap opens and closes, the voltage output of the flap position sensor changes. The vane-type mass airflow sensor does not measure air mass. In other words, there is more air molecules present at lower temperatures than there are at higher temperatures. For this reason, this older mass airflow sensor type also incorporates an air temperature sensor within the actual unit. This air temperature input is used by the ECM to fine-tune the mass airflow input value. The hot wire mass airflow sensor is a device that measures incoming air by the amount of current flow needed to maintain a specific temperature across a hot platinum wire element. As the air enters the intake duct and cools down the hot wire element, the mass airflow sensor circuitry will increase or decrease the current needed to maintain that specific temperature. The change in current is then converted into a voltage signal, which is then used by the ECM as a signal for airflow. Also remember that the voltage output signal produced by the hot wire mass airflow sensor is directly proportional to the amount of air entering the engine. So that, as airflow increases, so does the voltage output of the sensor unit. There are various types of mass airflow sensors using the hot wire principle. In this photograph we see a mass airflow with multiple hot wire elements. Regardless of the type, they all work the same, which is by changing the current across the hot wire to maintain a specific temperature. The first step in testing any mass airflow sensor problems is to analyze the barometric value on the scan tool. In our test vehicle, a Ford, the barometric reading should be at around 159 Hz at sea level. Always make sure to look up the proper specifications. Secondly, also using the scanner, analyze the fuel trims and the mass airflow sensor PIDs. As a rule, most mass airflow sensor problems tend to make the engine run very lean, since the mass airflow sensor cannot detect the actual amount of incoming airflow. Normally, the mass airflow sensor output should be at around 4 grams per second, but always consult proper specifications. Generally speaking, the short-term fuel trims will always stay at around 0%, and the long-term fuel trims follow in closely. A long-term fuel trim value, above or below, plus or minus 10% is indicative of an open-loop air fuel mode, and possibly a mass airflow sensor impending problem. Typical long-term fuel trims during a problem with the mass airflow sensor are between 18 to 20%. One of the first things to do whenever testing a mass airflow sensor is to pull out a wiring diagram. Whenever reading wiring diagrams, it is always useful to highlight the 3 main aspects of any circuit, which are the power, ground, and signal circuits. In our test vehicle, 2 separate grounds are used, the sensor ground and the mass airflow signal ground. The power feed, seen here in red, is used for every aspect of the mass airflow sensor operation. And the signal circuit, highlighted here in blue, is the ECM input for airflow. Step number 4. Prepare to perform all electrical tests, following the wiring diagram. These are the power feed, the two grounds, and the signal circuits. First, clamp the black digital multimeter lead to a suitable ground, either chassis or battery ground. Then, crimp the red digital multimeter lead to the mass airflow sensor power feed wire. With the engine running, full system voltage should be seen. Be aware of the fact that excessive ripple, caused by a defective battery or alternator diode, could have disastrous effects on the mass airflow sensor output signal and therefore on engine operation. Any alternator or battery fault may also have a huge impact on the rest of the sensors, computers, and related actuator circuits. Then, connect the red multimeter lead to the mass airflow sensor ground circuit. This first ground circuit is used to drive the hot wire side of the mass airflow sensor. A second separate ground is also used for the mass airflow sensor signal circuit. This is done to prevent ground noise from entering the mass airflow sensor signal circuit. When testing any ECM ground circuit, always follow the 100 mV rule, which says that any ECM non-floating ground should not drop more than 100 mV between battery or chassis ground and sensor ground. This 100 mV rule can always be used to test any computer ground circuit. Then, proceed to test the mass airflow sensor signal ground by tapping into its respective wire and following the same 100 mV rule. It is always a good idea to grab the mass airflow sensor ground in order to detect any ground noise entering the mass airflow circuit. Since this sensor ground is a return circuit for the mass airflow sensor, any problems here will have disastrous effects on the output of the mass airflow sensor. Corroded battery terminals, defective alternators, and batteries are all sources of excessive ground noise.